Luite. I'm from the Netherlands and I'd like to give a talk about the missing Haskell DevTools. I work at IOG, which in the platform engineering team, our main application, our main big Haskell application is Cardano node, which is a blockchain node. It's a distributed system and it does all kinds of things at the same time. Like peer discovery, it has a Lambda calculus interpreter for running smart contracts. It has a database for all the blocks that all the contracts can query. There's quite a bit of interesting high performance coding in there. And the platform engineering team, they make the build stuff, the build environments, and I'm in the GHC side of things. So sometimes we fix performance issues with GHC, and I also work on the GHC integration with our Haskell dialect that we use for writing smart contracts. It's called Plinth. It's a strict dialect, but we have a GHC front end, and it compiles to our own untyped Lambda calculus intermediate language that we upload to the blockchain and can run there. And yeah, we use quite a bit of Haskell. I think we have at least 60 Haskell developers. Then we have some formal methods team that use ACDA sometimes to flesh out protocol specifications of crypto systems. And we use ACDA, the Alonso Haskell generator, to make runnable Haskell code. And sometimes we include that in our test environment. So have a specification, a reference implementation that works well, and then our Haskell teams will build a high-performance implementation for our production deployments. And well, that's my current work in the Haskell world. My first big project that I maybe some people still remember me from is DHCGS. Used to be a standalone Haskell to JavaScript compiler. A couple of years ago, we integrated into GHC as one of the backends. For that project, I also had to build an external interpreter. Like GHCI used to be integrated into GHC, and it meant we could not do any template Haskell for cross-compilation, and JavaScript is cross-compilation. Profiling is also cross-compilation, so it turned out that this was quite of a generally useful tool, so that got integrated into GHC much earlier than the JavaScript backend itself. And recently, when I'm doing like upstream work, then it's mostly either bug fixing things that we run into, small performance improvements, and some things that I've done myself were working on the interpreter and debugger. Like we were using Haskell language server. We found out that sometimes it could not load certain files because we were using primitives like unbox tuples. And template Haskell in the same modules, and the interpreter couldn't use those, so I implemented those, and now that's been used as some infrastructure for more Haskell tooling. That's my background. The current talk is really about the things that I've been asked to do. Like if every time we make a big upgrade of our software, we go through performance validation cycle, and sometimes with Haskell we rely on lots of compiler optimization. We expect the compiler to be smart. And sometimes it's smart in different places, so it turns out that we have some regressions and we have to look into what's going wrong, and every time I usually find the answer why it goes wrong, but I always feel a bit like, what if next time I can't find it? There's no principled way or no way to really explore the program. So it's, the things that I've been asked, like why are we slower in certain requests, the program gets maybe moves work from one side to another, and Haskell is particularly complicated because of laziness. So in most other languages without laziness, you kind of know when something is being processed. It's in a certain call stack, and there's not really as much that can go wrong. And we don't really have good tools for analyzing where things come from. So for laziness, or if you have, say, increase in CPU time in the garbage collector, then maybe we are holding on to more data long term, it gets promoted, and it uses a lot more cycles, and yeah, where does it really come from? So I felt a bit uneasy about this, and this whole thing comes from a project that I did investigating something that held up our release by a couple months, and we found the problem fairly quickly and then fixed it in GHC, but still I've wanted to find it quicker next time. So I think we'll go through the main question of a program that is using more more time than we expected to. It's really how did we get there? Maybe our program is using more data, more time handling a certain kind of requests, and we need them to be fast. And yeah, we want to answer the question like what's our call stack? What's the reason that we're spending more time there? And for other languages like C, it's kind of straightforward. Like if we have a simple function with a few, a program with a few nested calls, then we can just use GCC and compile it with debugging information for all the function addresses in the executable. It will know the name where it comes from. The compiler will put enough information on the stack to mostly get you what you want. This program that just computes some hash, or it's just a toy example. If you load it into perf, then it will mostly give you a call stack or samples that will be fairly close of what you expect. Sometimes some stack frames will be missing, but they're usually mostly complete. Like there are a few in between. Let's see if we. So in this case, if we go back to the program, we have mix and hash step that are no inner and hash step that are missing from our basic perf sample. And in this case, if we look at the assembly code, there's one tail call and there's one thing where it doesn't set the. I think it's an inline function or something like that. But even then we can use dwarf symbols. Dwarf has a bit more information. It does not just have the frame information, but it actually has some information of where we are in the frame. It uses the exact return address, and if a part of the call frame is in line from another function, it will be able to reconstruct pretty closely what we've been expecting. And this is a generic tool. It works for C, for Rust, C++, and yeah, a couple of years ago, Well-Typed tried to make more dwarf information available with G8C, and it worked to some extent, but we never really got to the point that it was actually useful, maybe. And the rest of the talk will be a bit about what we do have and why it doesn't quite work. This is the actual assembly code, but I don't think it's all that important. So it's more about Haskell. So in Haskell, and the same goes for most functional languages, and it doesn't really matter if they're strict or lazy, we have many calls that never show up on the stack. If we have something like the function double here, it's just using unbox types, since that makes it a bit easier. This is something that's just a tail call. If we compile this thing, it will jump to X, to the plus function, and pass it those arguments. And that means that if we are in our performance analysis, and we, in general, when we run performance analysis, we do sampling of the program states. Another way we could do is by tracing, but tracing in most languages, especially functional languages, we have very short function calls. If we have something where we have to keep track of where we're entering and leaving a function, that's way too much overhead. So in practice, we always use sampling. So in this case, if we use double or and then double, both of them are tail calls, and that means that yeah, they don't show up on the stack. The way that perf reconstructed our stack trace was that it could walk the stack and it could find something where it is. And sometimes it's easy, it's just the frame pointer or something that's immediate, and sometimes we need a little bit more debug information of where exactly we are. But in G8C or in Haskell, it's just not there at all. And oh wait, this is the actual generated assembly code for these functions, and it's really just moving some arguments around and then jumps to where it's going. And there's really no other way around it. We could, yeah, this is the efficient way to do it. We don't need to use the stack, and if we did grow the stack, then there are many situations where in a functional language you use some sort of recursion instead of a loop. So we would grow the stack indefinitely or non-constant, and that is, yeah, just not acceptable. So in many ways we don't really have an option of doing tail calls. And it's not just functions with unlifted arguments. Like even if we have something with lifted things, we still have the same problem. In this case, if we have the first argument, it will branch on that and then do something depending on the value of that. It does depend on the evaluatedness of the first argument. So if there's something where, but it's not called x here, but since we pattern match on it directly, but if we had x and we had to evaluate it from a normal int, then we actually had a non-tail call. So if for the next function, no wait, this is the assembly code, but you can also see that it's just a test and it will jump to one label for one a branch and to the other label for the other. It moves the arguments into place and it jumps to the tail call, to the function. And but in some cases, well, we do get stack frames. In this case, we have to evaluate the head of a list. We branch on whether something is a cons or a nil, and in that case, what we do is we usually we push whatever we need at the other side when we have evaluated what we need, and jump to the evaluation of the thunk. And then when we get it back, when evaluation of a thunk is done, the function will jump to what's on the top of the stack, and then we continue operation. So we push, often it's, people call it a continuation stack, but it's really just a deferred way of calling things. But it does mean that what we have on the stack is not guaranteed to be the stack of functions that we've been calling. Quite often things are missing, they're being late, but there is something. And if you have more, it's still something that's sometimes usable, but it's not nearly as complete as what we were expecting from C. So here we have this function. It actually pushes something on the stack. Since the stack is growing dynamically, we also have some things that check the size of the stack, and we have to jump to the storage manager if there's more work to do. But yeah, that's pretty much what STG stacks are. So they are a bit more complicated, but they're also very incomplete. And that's the main thing where they're kind of less useful. But there's another thing that makes them less useful for tools like perf. Even if we have more dwarf information, the stacks in Haskell, they start very small. We have lightweight threads. We can support thousands of threads at the same time. So every time we push something to the stack, we check whether it's overflowing our block. We allocate a new block, and in the end we have a linked list of blocks that is the whole stack. And standard tools like perf, even with dwarf information, can't quite unroll that whole stack. And often if you're in a long-running program, you kind of want to know the root of the problem. Am I handling some request? Am I somewhere else? Maybe the last 10 frames on my stack, they tell me something, but they don't really tell me where I'm coming from. So stacks are there, they're incomplete, but with standard tools, they're even more incomplete since we only have the last chunk. And then also there's another thing, like much of our generated Haskell or assembly code is heavily optimized. We rely on specialization, and so attribution of where in our source code do we really show what is costing us time. That's also kind of a hard question, but that's kind of outside of the scope of this DevTools talk. But I just wanted to mention it. Now we do have a few other options, like for backtraces and error handling mostly. We have explored a few things in Haskell, and the question is, can we maybe use those better for debugging and profiling? And the answer, well, it's not really all that good. So we have the Haskell stack constraint, and you can make better exceptions with those. It's quite useful to not have just a prelude.undefined when your program crashes. But if we want something where we actually want to investigate performance, then it's something that's quite expensive. This is implemented in GHC as an implicit parameter, and every time a function with this constraint is called, it's handled in a special way by push call stack. And push call stack, well, it allocates a new heap function. It's basically building a linked list of stack chunks, and that's a rather expensive thing compared to just pushing a few words on the stack that we have in other languages. let's see. So I ran a small test of these two functions, and if you call them many times, then it just allocates 1,000 times more, and that completely screws up your measurements and everything. So it's useful for getting better diagnostics information sometimes, but you definitely don't want to instrument all your code with this. In GHC, we sometimes have this thing, but then renamed as hasdebug call stack, and in production runs we completely disable it. It becomes a unit constraint, and in debug runs we accept some slowness, and it becomes a Haskell stack, an actual constraint. But yeah, if there's this much overhead, it's basically useless for profiling. Also, Haskell stack constraints, they have no way to handle recursion or recurring stack frames. So if you have something that processes a long list or does some stream processing, then yeah, you will use unbounded stack space while you were using constant stack space before. So this is not something that you want your instrument your whole program with. Then the other traditional profiling method for Haskell is cost center stacks, and there's a similar story to those. And there's something else that's also interesting. The question is what problem they answer. And cost center stacks, they were conceived as a way to answer where time is being spent in a sort of lexical way. If I'm writing a server that handles HTTP requests, and one of my requests is suddenly slow, then this is a time-critical part of my code. So I really want to know what if time is being spent there. And if I have this small program which has an expensive computation, it's supposed to run this computation in the cache warmer, but it doesn't. Then actually what cost center stacks do is attribute the cost in a different way than I want. Since lexically the thunk is being created at the cache warmer side, and the rules for cost center creation is attributing cost to the place where the thunk is being created. And that is, if you have a batch system and you want to know like the place in your source code where you can find where is my thunk being made, then that's fine or maybe quite useful. But if I have a running system like Cardano or a server that handles requests, and there are some things that really need to be handled fast, then yeah, it's not really the question we answer. It's not wrong, but it's not answering the right thing. And also it's very inefficient. Like look here, the example for this thing, it's completely attributing the costs to the cache warmer, even though the actual computation runs under the HTTP handler. Cost center stacks do solve one of the problems that we had with call stack. If you push the same frame again to a cost center, you have recursion, and it will refuse to duplicate frames. So you do solve the problem of infinite stacks, but the result is that it's really expensive. Every time we enter a function with a cost center stack, we have to figure out whether we already used a child node of that stack. We have to reuse existing stacks and add something to the number of entries or a number of allocations under a certain stack. So all my programs get way and way slower. And there used to be an additional problem. Cost center stacks were inserted quite early, just at the source level, I think, just before running the simplifier. And if we want to keep the cost center stacks correct, then there are certain transformations that we just can't do. So sometimes our program would not be optimized as much, and that's kind of horrible. My program is not even running the same allocations or something. It's not just slower, it's slower in unpredictable ways. So there have been some, oh wait, I skipped over something. There have been some things that have been done to fix that. But first let's go over how cost center profiling works on the heap side. Since we want to attribute costs to places in the source code where they're being allocated, we have maybe, when a thunk is being created, it has to record the cost center where it's being created. And that means that in every thunk, in every heap object that we have in the Haskell runtime, we have 2 words of overhead of basically recording the cost center state. For all functions, we have a cost center stack. For all thunks, if we evaluate a thunk that's been being created somewhere, we switch to that specific cost center stack. That's the rule. If we have a function, then we combine the cost center stack with the existing function that we have. And it's all quite a neat system, but it's very expensive. So that makes it a bit hard to use. There's some ways that have been improved, even though they don't improve the constant factors very much. We have late cost centers now in recent JHC, which delays inserting cost centers until after the simplifier has run. So at least it means that the simplifier does not make different decisions. But as we can see here, it makes it a little bit faster, but it's still 5 times slower than my normal code in really simple code. And the bigger your program gets, the bigger the cost center stacks are, and the longer it has to search for reusing existing cost center stacks. So this is something that is sometimes useful. In particular, it's quite useful because it records where things are being created. And sometimes that's information that I actually want. And we have not really talked about that yet, but that's something that I'll come back to in a moment. So there we have basically the 3 methods that have been available for a longer time in JHC. We have the STG stacks, the actual running state of the program. We have some call stacks, but since they are using incomplete frames, they're kind of missing information. They don't work very well with standard tooling because of our chunked stack things, and because we use registers and calling convention. That's not very common. So yeah, that's something, but at least it's fast. It's there's hardly any overhead. We spend a little bit of time sampling our stack and constructing where we're from. We have Haskell stack, but it's very inefficient, and we can't use it for instrumenting everything, since we will get unbounded stack usage. And we have cost center stacks that are very detailed, but sometimes answer the wrong question and are quite expensive. So recently, there's been a move towards a bit more efficient profiling. We don't want to use the profiling runtime, but we want to store more useful information for Haskell programs in the performance, like the normal production runtime for Haskell. And the idea is to fill in the missing bits in what we identified so far. And in, I think, JHC 10, or it might be 9.14 already. I think 9.14 introduced the primop, and how much do you have?
Another 15 minutes.
Good. JHC 9.14 introduced a primop to explicitly push a stack frame to your STG stack, which means that if you then sample your stack, you at least find something back. You can use part of your program, like I'm in an HTTP handler, to show up on your stack. And there's even an annotation in there. So you can find on your stack, you can say, I'm handling a request for this client or for this resource or something like that. And that's a quite useful thing to fill in things. It's still a manual thing, but it turns out that all the automatic methods that we had were not really getting us there. So
the type of this take hash?
I think it's on the next slide. No. Oh no, I did not.
Is that a state hash one, or?
Yes. So it's annotation to I think an IO to but the unboxed one. So state hash to tuple of state hash and A to. So it just transforms some IO A to another IO A, but then so with something in between.
It takes an annotated IO, so it sort of wraps it. Right?
Yes, it's a wrapper. Yes.
Okay.
And let's see. And the other thing is, yes, I'm combining two things that I should have in 2 different slides. So IPE is basically what dwarf symbols are, but then specific for Haskell. It's debugging information for closures, for stack frames and things. So annotate stack is something that is orthogonal to that, but it helps. The idea is we use the production runtime, we add stack frames where we need, and we add debugging information to all the closures, all the other stack frames. We know we want to know where they come from. So when we have write a debugger, then we can, or a profiler, I mean, when we sample, we have enough information to know where we come from, and we know also how it correlates to the source location where we came from. And there's some other trick that's been used. Here we have some program that allocates 2 constructors, and say we are looking for a memory leak in our program, and we want to know where our data came from. Sometimes we can use our type profile and we can just know there's maybe only one site where we allocate something, and we can see why it's not being forced or not still being retained. But the just constructor is so common that just the info table does not really give us much information. But some of the new options in recent GHC also allow us to split debugging information by construction site. So here we have two places where we construct a just constructor. We can attach some IPE information. Info table provenance entry is what it stands for, but I'm not sure if that's the most useful name. But in this case, we have two constructor sites. We can, at runtime, when we allocate a just object, the just heap object will be one word for the header and one word for the payload. And the header is just a generic constructor object. It's the first constructor, or the second constructor. Nothing is the first constructor of some data thing that has one word, that's one pointer of payload. And we can just, it doesn't need to be the same for every just. So in this case, if we use f-distinct constructor tables, we can allocate something with the source location per construction site, and that allows us to find where we allocated some data. That's useful, a bit more, but it does not quite tell us as much as what we did for the cost center stack profiling, since it gives us sort of leave node information. We know where it comes from, but we don't know why it comes from there, who called it. And that's something that is in the thing that led to this talk, something that got me a bit stuck. So let's see. So in this case, what's being produced for this is two info table provenance records. They end up in your executable, and there's some backtrace like where from, and there are some other things that are in the base or GHC internal library that allow us to find where things come from, and our debugging tools are also increasingly using this kind of information. Let's see, annotate stack. Here we have it. So I had the slides in slightly different order. We take an annotation, or we take a node, and we transform an IO action to a new wrapped IO action, and this thing will be on the stack while we run this action. And if we then write a profiler, then we find this thing somewhere on the stack with this node, and we can reconstruct our profiling from this. Well, this is how you use it. You can use it just to annotate certain parts of your program. In things like Cardano node, we can use a top-level stack frame to indicate what kind of thread is going, and then certain parts of the state machine that the thread is going through will be annotated by other things. It's not something that we've been using in very detailed way.
You can put any Haskell object as an annotation.
I think so, yes.
So how do you read it back?
I forgot exactly. There might be some constraint in there. I think this is just in the example. I think the primop allows that, but the normal user API does not, or should not.
Yeah. But then you need a single kind of annotation throughout the program.
Yeah, I think so, yeah.
So
there's probably something wrong with my slide here. So for lightweight profiling, I think if we want to know where we're coming from, we can sprinkle our annotations that probably do need some more specifics than just a random type n in the program, and we can eventually find out if we are using time somewhere, where it comes from. If we have a sampling profiler, then these will end up in our traces. And we have actually the kind of program that's called GHC stack profiler. It will use these, it traverses the stack, and it dumps all the stacks to the event log. The event log is something else that we have in recent GHCs that's now always available. You don't need to explicitly link your programs with event log anymore. So it's a binary logging mechanism that allows us to inspect Haskell programs remotely, or you can log to a file. There is also some things that connect an event log to OpenTelemetry, and we can wire it up to Grafana dashboards and all kinds of fancy things that people have been using in large-scale productions. But yeah, that's half of the story. The other thing is laziness, memory leaks and things. With this fast debugging, we still don't quite have a way to find out where things were allocated. With stack, with cost center profiling, we used to have it, but with the IP programming, we don't. And there's another thing that's well-typed implemented a couple of years ago, I think 2 years, 1 year. It's called eras profiling, and that's a very simple form of profiling where there's just really one operation, set user error, also get user error, and that sets a program global constant, and everything that's been run, being run during that constant gets annotated with this error. So if I allocate something, then it will be stored in the profiling header of that tool of that closure where it's being created. So if I have, say, a web server and I see that it's being objects from a certain request that I've long done with are still lingering in the memory or something, then I can see that clearly something is wrong, and I can then find out how they're being retained and figure out the problem. And this has been used with quite some success to figure out memory leaks in GHCI and Haskell language server. But there's one big downside compared to everything we had before. This requires the profiling runtime. And that makes it immediately useless for live monitoring and actual critical performance monitoring due to the way it's implemented. It stores a word, the error, in each closure. This is basically how it works. We need the profiling runtime. But actually we don't. And I have a prototype implementation of that. If we change how the error is being recorded, we use the storage manager, and the storage manager allocates pages. Each page has a block descriptor, a block. Each block has a block descriptor. And since errors are something that change slowly over time, we can group usually things with the same error together. It's not like a function call stack or something. It's something that stays the same for a while. So if we, instead of recording the error in each closure, we record it at the start of the block, and when we switch an error, we close the current block, we open a new one. Then we have a bunch of error consistent things grouped together. We update the storage manager to only evacuate same error blocks to same error blocks, combine them if they get a bit empty. But yeah, that works way better. And I've been using this for a bit to experiment with this. It's fairly new still. But
a north slide?
What?
OGC 10.2.
Oh, 10.2. Yeah, so no, it's now in prototype stage. 10.0 I missed the merge window for, and 10.2 might actually be ready. It's a question mark, since this is, this is something that affects the storage manager more than current errors profiling. That is something that's just reusing a word that was already in the profiling header. And the normal hot path for non-profiling would still be the same, but this requires a few hooks in the garbage collector that are a little bit more complicated. So we'll have to review this code and see how this works. But I'm quite excited to at least find out where things are being done. And you can, the error is just like in the normal errors profiling, a word that is set by the user. I think, and I've also implemented that error should really be something that should not be program global, it should be thread local. Since I want to have one thread that does a certain task and everything should be stamped with that task, I want to find inconsistencies there. So those two changes I'd like to make, and with some luck they might be in 10.2, or maybe it will be a separate mechanism that will have a different name in 10.2. And with those combined, I think we have a fairly good way to do reasonable performance profiling. If I don't know where I'm coming from, then I can use the annotate the stack with a little bit of information, and for the larger coarse-grained finding out where I'm coming from, it usually helps me enough to get there. And also I can quite clearly see where data is coming from if I'm retaining things in too long, for example. So yeah, the workflow that I've been trying out is basically just that. We use with stack frame and with user error to annotate our tasks. We use the non-profiling runtime, the performance runtime. We have fairly little slowdown, and we can look into this. Everything should be connected with the event log, I think, but we still need, and I think that's the title of my talk, we still need something to process all the data. And while I was working on GHCAS, I found it so easy to just pop into Chrome, open the Chrome DevTools, you could explore everything, and that was so easy. Sometimes I even wrote Haskell programs and didn't know what was going on. I would compile them to JavaScript and open them in Chrome DevTools. They were much slower, but you can see what's going on. And with our Haskell tools, they're kind of, they're Spartan. So I think we need some better tools that can run on top of this. We have the event log, we have a few things that annotate our program, and then we need to collect all the information from our running program and present it in a way that is explorable, that we can find out what's going on. And GHC debug works nicely. We have event log to HTML, it's static. We can get some information from that. We can get some JSON profiling reports that we can load into SpeedScope. It is all quite fragmented, and it's not something where I can really explore what my program is doing. And this is basically the second part that I've been working on recently, and I'd like to give a short demo. Do I have a few minutes? Yeah, to show what it's like. Let's see. I have this in VS Code. So basically the program I've been writing is a combination of what GHC debug is and an event log processor. The event log gets all the real-time information from the Haskell runtime. It works the same way as GHC debug, where we have a connector thing part that we load link into our program. It's a bit more user-friendly. This is basically how I think I want to use tools. So in this case, I loaded up into a pre-wired demo, but when I start my program, my Haskell program, it's writes a descriptor file in a known location, and that says the protocol version, a socket where it can communicate with the inspector, and then the inspector can discover it. I have already here in my VS Code plugin an example, but I can't quite open that since there's a bug in how it finds executable, but once I release it, it will work. I'll open it directly now. There's a text user interface like GHC debug, but the main thing that I've been working on is the web user interface. So once I open this, it finds the running Haskell programs. This is just a test program. It starts in the timeline view. If ever anyone has used SpeedScope, then this is basically what they've been doing. All the threads, they show various colors depending on what kind of reason they're blocked on. All the capabilities are there. You can filter threads. Everything is basically served over HTTP. It's just everything can run remote. The event log is consumed over a Unix socket normally, but in principle it does not really have to run on the same machine. Some of the functionality is better when it runs on the same machine, since similar to GHC debug, it can inspect the running state of a program, so it can collect the heap from a program. And I think that in the way GHC debug does it is it sends the heap from the Haskell program, but that means if you have a pointer that is kind of broken, then you can crash the program from inside. So this program is a preferred method, actually requested from the outside. So the inspectee grants access, and then from the outside you can read the memory directly. There are a few other views that I have. There's an event log view or just VM raw events. You can filter them or group them. And now I just have all the events grouped together. It's a bit slow. It runs on a server in the Netherlands, and yeah, I should have known that. There's some flickering that I still need to do. Event log can be huge, like 16. I ran into the 16 million pixel scrollable area limit there, so I had to work around that in the virtualizer. It only requests part of the window that is in view, and there are a few other views that are like this too. While we're running, if we have our program run compiled with profiling, we can get all the cost center stacks. So even though I think they're really slow, they're still sometimes useful information. We should expose them in a better way than completely static. We also have flame graphs. They update. I hope they update in real time, so we can also drill down on the stack and we can get some information there. It's still not quite as polished as SpeedScope. Maybe we can integrate SpeedScope at some point, but I'm not quite sure yet. Since this is something that needs to update real time, it gets one update per second, and SpeedScope is something where you really prepare a big report and then render it as a big thing. So there's still lots of work to be done.
You could collect a report, you could collect a report.
Oh yes, yes. I think that should also be a button, and then we save the final report, and then you can do the detailed digging. But I think this should be a tool that's a bit like Chrome DevTools, where this is where you explore, and then maybe if you need to dig deeper, you collect a report and you write some script or something to do the deeper analysis. But what I really was missing for Haskell was this basic thing. We also use have Tiki counters. Those are a low-level profiling mechanism that hardly people use, but it was very easy to add since these things exist already in the event log. Most of the things are really based on collecting all the events from the event log and working through them and displaying them in a reasonable way. You can also pause the program just like DHC debug. Then you get a whole bunch of other things. So you can run a consistency scan on the heap, which means the inspector now has to request all the heap data from the running Haskell program, a bit like DHC debug. Now it ran a consistency check. There are some suspect black holes, and I think that's actually a bug in my scanner, or there's some transient state where there is something where it does not quite know that it's actually correct. I don't think this is a DHC bug. But it's very easy to write heap analysis things. You just request all the blocks, and I think here you go with this should actually have all the blocks already, since it's also loaded them for the consistency scan. Oh wait, I can select the block and I can browse through all the hex data. It's rendering a bit wrong now, since I was adding all kinds of annotations to overlay that actually something is the start of a byte array or a closure, and then you can jump to the source location where it comes from. There are so many things that you can do, and we only had a few weeks to prepare this. So this will be my main project at Zurich Hack. So if anyone's coming to Zurich Hack, I'll try to get this released before then, and then hopefully get this ready, because you can also get a list of MVARs and everything just to inspect what your program is doing. And I'm just throwing the whole kitchen sink at this. So yeah, that's pretty much it. The main thing I think is that it should be easy. So I wrote VS Code extension, and it automatically finds all the running programs. You can just double click on it and explore it a little bit. And if you don't, or you don't need it anymore, you just resume the program. Now it runs again, and I can detach, and it's really just a normal Haskell program. The only thing I really need to do for my client side, my package, is adding this Haskell inspector connector sub-library, and it will do this, make it discoverable automatically and a bit more inspectable. And that's pretty much what I've been doing. So we can go back to the slides. And yeah, this would be the conclusion. Lightweight profiling that I've been working on that's actually useful is still kind of incomplete, but with all the bits, even though it requires a little bit of manual annotations, we can get a quite good information, I think, of Haskell programs now. At least from the server, from the program side. Presentation, like on the client side, the DevTools themselves, they're still quite rough and still quite early, but they're fun to work on. So yeah, that's pretty much this. I hope Haskell Inspector will change the things a bit. It's not really competing with the other impressive projects that are going on, like the Haskell debugger that Rodrigo and WellTyped are working on, based on DHC debugger. This is something that works on compiled Haskell programs, like for performance things, and it's not really meant or intended to be a step-through debugger. There's also not any replacement for Haskell IDE engine, or what Haskell language server is what the current name is. So it sits a bit in the place where GHC debug and eventlog to HTML and some other smaller tools are sitting, and I hope I can maybe get some proper tooling there, and maybe reduce a bit of the fragmentation, and at the same time add the features to GHC that we actually need to get us the information. Cool. That's my talk. Is there any questions?
So we don't have too much time, so I suggest that we start eating the pizza, and at the same time we can ask a few questions to Luite.
Okay.
Does anyone have any questions? Yeah.
I do.
I don't know. How are you supposed to? You mentioned that internally you were using a string variant of Haskell. So are you able to actually inspect where the allocations happen, since you don't have to track where it was forced and where it was actually instantiated, the thunk.
I don't think that's true. So the strict variant is used for smart contracts, and they tend to be quite small and self-contained. So they're more like a batch system. We run one operation through them, so it's very clear where they're happening. And usually what we're doing when we're analyzing progress there is running them in the UPLC, is what our untyped lambda calculus thing is called, in the interpreter directly there, and see how many cycles it takes there. So these are not the big programs that I'm aiming this tool for. So.
Thank you.
Any other questions?
Well, I have tons, but maybe I'll take them online.
That's
fine.
Is it released yet?
No, I have to admit I just claimed the name today on Hackage by uploading a release candidate, and I still need to clean up quite a bit. I'm hoping to get it released in, like, not really released for end users, but to be able to collaborate on by time of Hackage, which is in a couple of weeks in Switzerland. So I hope to see everyone there.
Great, I'm looking forward to it. It looks really nice to use. Okay, let's thank the speaker again. Thank you.